What is a logarithm? A logarithm has to do with exponential functions. In fact, log functions are the inverses of exponential functions. So, in essence, a logarithm is just a power. So, power. What does that mean? Well, we have 2 squared, or we have 2 to the 4th. That's a better example. The power is the small number, the number that tells us how many times we multiply it by. So the logarithm, when we do a logarithm problem, we're basically going backwards. We're trying to find what that power is. So we might say the log 4 of 16. Here's what I'm asking. I'm asking, what is the power that makes 4 into 16? What power do you raise 4 to get to 16? And the answer is 2. So when you read a log, you think the power that makes 4 16. So let's think about a couple others before we get into abstract views. Say we had the log base 2 of 8. What is the power that makes 2 into 8? 2 times 2 times 2 times 2. How many times would you need it? It's 3. Logs also can work in another kind of cool way. Say we have the log base 25 of 5. What is the power that makes 25 into 5? Well, it's actually the square root, right? We would take the square root of 25 and get 5. So the power that makes 25 5 is 1/2, because that's how we write square roots using exponents. So a logarithm is just a power. Let's look more closely at what all these pieces of a log is. A log has a few different parts that we want to be familiar with. First off is that b. That's called the base. The x is called the argument. And the y, that's just the result, or whatever it is you calculate. In this case, it ends up being the power, or the exponent. So if we were to think about this as an exponential problem, the base, b, the power is y, and the answer there is x. So they're just inverses of each other. We're looking for the power. Usually we're looking for what the evaluation is. Let's compare a couple tables. Let's say we had y equals 2 to the x. So let's start with -1, 0, 1, 2. 2 to the x, and we evaluate it for -1. We get 2 to the -1, which is 1/2. 2 to the 0, which is 1. 2 to the 1, which is 2. And 2 squared, which is 4. Now let's look at log base 2 of x. Now what we're doing is we are looking for power, or we're looking for the powers. We're not getting the powers, we're getting arguments. So the log base 2 of, let's start with 1/2. What is the power that makes 2 into 1/2? It's -1. Let's go to 1. What is the power that makes 2 1? 0. What is the power that makes 2 2? 1. What is the power that makes 2 into, 4? It's 2. Now if we look at these two tables that we have the table for y equals x squared, 2 to the x, and we have the table for y equals the log base 2 of x. They're inverses of each other. So if I were to ask you to find the inverse of y equals 2 to the x, the inverse function is the log base 2 of x. These two are closely related. We're going to be looking at a lot of properties of logs and ways to solve logs, And it's all going to relate to the properties of exponents. So now let's do a little bit more evaluation and look at a couple special types of logs. We spent a lot of time looking at the log base 2, so let's move on to the log base 3. Let's say we have the log base 3 of 27. I'm asking you for the power that makes 3 into 27. 3 times 3 times 3 times 3, how many would you need? It's 3. Now, what if we were to look at a problem where I just said the log of 100? You're going, what's the base? I don't know what to think. Well, when you see a problem written like this, when you do not see a base written down, that means that the base is 10. This is known as the common base. It is used a lot in computer programming and scientific notations, and so scientists and mathematicians have gotten to not even bothering to write it down. It's understood the base is 10. So you guys will be super smart looking mathematicians and scientists when you'll know that the base is 10. It's common knowledge. Come on. There's another special base. It has to do with the natural log. The log base e of, let's just say, x. The log base e of x. E, we've looked at already, is that irrational number that occurs a lot in nature. So we can write this expression as the natural log ln of x. When you see this, it's referring to the natural base. So this is the natural log. The base would be e. That will come into play occasionally, but when you see a natural log, you treat it just like any other log. It's just the base is e instead of 2 or 3 or 10. So let's evaluate a couple things. Let's look at the log base 5 of 25. Remember, I'm asking, what is the power that makes 5 into 25? 5 squared is 25, so the power is 2. Or how about the log of 10? Oh, remember what the base is when it's not written down. This means the log base 10 of 10. What is the power that makes 10 10? 1. Okay, how about the log base 64 of 4? What is the power that makes 64 into 4? This is a little bit tricky. Because 64, we're going to 4, really we're taking a root. How many times does 4 go into 64? 4 times 4 is 16, times 4 one more time is 64. So 4 cubed is 64. That means that 4 is the cube root of 64. And remember, cube root means the power of 1/3. So the log base 64 of 4 equals 1/3. The power that makes 64 4 is 1/3. How about the log base 7 of 1? What's the power that makes 7 into 1? What's that power that makes anything into 1? 0. This is kind of a special case. Log of anything, the log base b of 1, is always equal to 0, as long as your base is positive. Let's look at, how about the natural log? What's the natural log of e? What is the power that makes e? Just 1. How about the log base 6 of 1 over 216? Okay, we're going to raise 6 to a power, and it's going to make a fraction. So let's just focus on the 6 and the 216. How many times does 6 go into 216? Well, 6 times 6 is 36. Times 6 again, 216. So we know that 6 cubed is 2/16. Now to make it a fraction, we need a negative exponent. So instead of cubed, it's -3. The power that makes 6 into 1 over 2/16 is -3. We could go on and do lots of examples like these, but there's loads of practice problems on Canvas and practice problems on the internet and practice problems that we're going to do. So we're going to move on after this and talk about a couple other unique features of logs. We had logs of lots of different bases and lots of different arguments, but let's say we have the log base 4 of -16. What is the power that makes 4 into -16? So 4 to the what equals -16? It's not a negative number because that's just taking a square root, or that's making it into a fraction. It's not a fraction because that's making 4 into, that's taking a root of 4. There's actually no solution to this. There's no power that's going to make 4 into -16. So one thing we need to keep in mind with our logs is that our arguments, what's in the log, so the arguments are always greater than 0. They're not even going to equal 0 because what is the power that makes 4 into 0? Not anything for that one either. So our arguments are always going to be greater than 0. And another thing we need to keep in mind is that our bases, these bases, are also going to be greater than 0. Another important feature to note about our bases is that our bases are not going to be 1. They can be fractions, but they cannot be negative and they cannot be 1. Here's why. Think about the log base 1 of 17. What's the power that makes 1 into 17? There isn't one. 1 to any power is always 1. And so it doesn't make sense to have a base of 1. It's never going to get you a solution. So these are just a few rules for logs that we'll be keeping in mind throughout all of the log experiences that we have. Our arguments are greater than 0, our bases are greater than 0, and not equal to 1. So earlier I said that logs and exponents are related to each other. They're actually inverses. So we can convert between the two. This is going to become handy when we start solving. So let's say we have the log base 4 of 64 equals 3. Well, if we want to convert this to an exponential form, we have the base, this is the power, and we have the argument, which is the result of an exponential. So 4 base, power is 3, equals 64. These are the same, just written in a different form, the log form and the exponential form. So let's look at a log form of, let's say the log base 6 of 36 equals 2. True statement. The base of this problem is 6. The power of this problem is 2. And the argument, the result, is 36. So again, same thing. We can also go the other way. We can go from exponential form into log form. So let's do e to the 4 equals 5. The base of this problem is e, so this is a natural log problem. The argument is the result, which is 5, equals the power, which is 4. So again, these are the same thing, just in different forms. The natural log of 5 equals 4 is the same as saying e to the 4th equals 5. Let's try another that way. Let's do z to the hw equals x. Yes, it's weird, but we can still do it. So this is a log, not a natural one, so I don't have to worry about that. The base is z. The result is the argument, which is x, equals the power, which is hw. Same thing, different form. Let's try another log one. Let's say we have the log of 1/10 equals -1. What's the base of this one? Remember, this is our super smarty pants scientist one. The common base, which is 10, the exponent, which is -1, equals 1/10. So we rewrote a log as an exponential. You can go back and forth from one form to the other. Like I said, this is going to come in handy when we start solving both exponential equations and log equations. So this was really just an introduction to logs. We talked about several different things, so let's do a little recap. For a recap on logs, remember that logs are a power. Logs are just a power. We are looking for a power that makes something into something else. So when we have y equals the log base b of x, we have the base, which is b. We have the arguments. And then we have the results. That's the power in this case. And we can switch between these different forms just by knowing what those three things are. We can write it as an exponential, writing b to the power y equals x, because logs and exponentials are inverses of each other. Now remember our rules about the argument and the base. The argument, in this case it's x, needs to be greater than 0. It's okay to be a fraction. We just saw an example where it was a fraction. The base also needs to be greater than 0, but it also needs to not be 1, because 1 is boring. 1 is always 1, no matter what power you raise it to. When we evaluate logs, we're just looking for that power. What is the power that makes something into something else? There were two special types of logs that I want to recap too. That was the common log, where the base is 10, and we just don't write it down. And then there was also ln x, which meant the natural log, which meant the base equals e. Both of these types of logs are, you can use them just like any other log with any other base. We're going to be looking at some properties of these logs, regardless of what their bases are, in just a little bit. In fact, that should be one of the next videos if you want to continue in this playlist.